Okay. Hello. Can you hear me? It's been a few weeks. So let me get started. Alright, so this is Junichiro Horikawa, and this is a tutorial live stream for Houdini. And this is 146th episode. Today I'm going to try to implement a so-called Eularian fluid into the using VEX method and OpenCL method. But I'm gonna try both ways and see the differences. Now I do have a reference to this implementation, which I referred from this page, 10-minute physics. This is where I see implementation of this Eularian fluid, which was written in JavaScript. So basically the basic code is coming from here, trying to implement this in Houdini in a Houdini way, try to use the Houdini functions, VEX functions as much as possible to as well as OpenCL to make it faster. Okay. Now, so that's that, and let me get started to implement the code. Now, before going into the detail, I would like to check his note so that we can understand the algorithm of this fluid system. Okay, so this is called Eularian fluid, and it can be used for liquid and gas, and this is a grid-based fluid, so it's not a particle-based system. You need to first of all set up a grid either in 2D or could be in 3D as well, which is also used in, I think, in Pyro simulations in Houdini. And it says it's also a compressive fluid, so that the liquid is not going to spill out. And its viscosity is equal to 0, so it's smooth. Now this part is pretty interesting. When you so each cell has its own properties, and in this case a velocity in which direction the liquid or the gas will flow, and in this case it is being visualized or expressed as UMV in 2D direction. Now seems like there are two ways to express the velocity. One is to use the center of the grid to express the velocity as is. But another way is to use the edge of the grid, combining the U on the left side and the right U on the right side, V on the top side and V on the bottom side. Now, in this code that he wrote, he is using the right side method using staggered grid. So each cell has its UMV on each edge. Now, the reason why he's doing this is because of this divergence. What needs to be done is that for each iteration on the simulation, you need to make sure that for each grid, for each cell, the outflow and inflow should be, and when outflow and inflow of each cell has to be, the total amount of outflow and inflow has to be equal. Meaning if you add all these values, it has to be equal to 0. Should be balanced. the amount of inflow and amount of outflow has to be equal. So that's kind of a reason why he is using this staggered grid to make the data structures of the fluid more easy to use. And because we have things like this, we need to create some optimizations in order to calculate the most balanced inflow and outflow for each U and V. And to do that, we need to use some kind of optimization method. In this case, we're going to use a so-called Gauss-Seidel method. In particular, it's also called as SOR, using over-relaxation method, somewhere written right here. So I'm going to implement that as well. And this part, I'm going to use OpenCL. Okay. So other than that, we have a velocity advection and smoke advections as well, which is pretty easy to do. You just need to use so-called UV sample functions in VEX, which is pretty easy to do. So the method, the algorithm is like this. First of all, modify the velocity value, add some constant velocity in some positions and or gravity, make the fluid incompressible, meaning you're going to calculate the divergence and make it balanced by using the Gauss-Seidel method, and move the velocity field for the next frame. And you keep doing this over and over, and you get this result. And currently I'm running this on OpenCL, so it's pretty fast, even with the density like 512 by 256, which is in total how many points? Like more than 100,000 points, which is a lot, I think. And you could also use you could also move the obstacle by yourself to try mixing on real time, which also works pretty much in real time, which is really cool. Okay. If you are not using OpenCL, then it's gonna be much slower. I'll show you it. So this is the one that I'm not using a OpenCL, which is only using VEX. In this case, it's gonna be really slow, as you can see. But it's a bit easier to implement because of all the useful functions. So first of all, I'm going to create a prototype in VEX for a smaller grid, then re-implement the same code, especially the optimization part, in OpenCL later to make it faster, like this. Okay, so that's my plan. In the end, you should be able to create something like this in 2D. And with not much cost, I think you could also re-implement it in 3D as well. But I'll keep that to you yourself. Let's just do this on 2D from scratch, shall we? Alright, so first of all, I'm going to create a setup, like all the sizes and velocities and stuff, the initial velocities and stuff. So let's do that. Okay. So first thing first, I'm going to create a geometry node. Then I'm also going to create a null node containing all the parameters that I would like to control globally. Okay, now I am going to start with a grid, which is going to be the base canvas for me to create the simulations. Now, first thing I need to do is to provide a number of points on X and Y direction. So let's have some values for that. I would like to test with a small number for initial testing. So let's make it, I'm gonna name it numX and numY as an integer. And let's set the range to 0 to 1000 for each. Okay. Now I'm gonna go with the small resolutions first. Let's see, 128 by 64. So you have like, no, I haven't used this yet. So let's copy this numX, paste it onto columns, copy the numY, paste it to rows. Okay. Oops. Now currently, because the X and Y number is different, there is a size difference on the width and the height for each cell, so I want to make it square. So I'm going to make the size aspect ratio related to these rows and columns. So to do that, I'm going to define the size of the width and calculate the height automatically using an aspect ratio. Okay. Set the maximum to 100. Let's set the width to 100 for now. Let's copy this, paste it to the X size of the grid. Then for the Y, first of all, paste the width and copy the rows, multiply the rows and divide it by the columns. Is that correct? Yeah, that should give you the correct height. Okay, so that each cell will gonna be squared shape. Okay, now to make it easy to control, I'm going to make the top left corner of the point to be set on the 0, 0, 0. So I'm going to use a match size to move the whole object. Justify X to min, justify Z to min. Okay, like this. All right. Now, next I'm going to also reorder the point number. Currently the point number goes from 0, 1, 2, 3 on the X directions, but the way I first created the code, it has to have the point number go from 0 to 0, 1, 2, 3 going to bottom Z directions instead of going X directions. So I want to flip the directions, not going from to the right directions, but going to the bottom directions. Go like this. Something like that. 0, 1, 2, 3, and so on. So to do that, first of all, what I'm gonna do is to create a number for each point to get the X number, X directional index number, and Y directional index number. Meaning, in this case, this will be 0, 1, 2, 3, 4 for x at x, and 0, 1, 2, 3, 4, 5 for y for each point. Okay, and I can use these informations to recreate the new point number and sort all the points based on those numbers. So let's do that first. This is the preparation part. Okay, so I'm going to use a point wrangle for that. So let's call this point initialization. Now, in order to set the x directional number and y directional number, I need to know what's the size of the x and what's the size of the y. So let's have that, which is num(x) and num(y). Having declared here, so let's copy this x and y and use these to get the x and y numbers. Now the x can be calculated by calculating the remaining by dividing it by the num(x). And as a result, you should be able to get the x for each point. Like that. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4 for which shows the number of columns for each point till the end. Same for the y. For the y, you can calculate it by dividing with the num(x) and get the floor number. As a result, now in this case a row number, you can get a row number as a y. Okay, so having those informations, you could now calculate the new a point number. I'm gonna call this sort. So what I would like to do is to go from top left to go downward and keep going to the right. So that will be ix multiplied by num(y) plus I at y, I think. So let's check. Let's review the attributes. So as you can see, it starts from 0 from the top right, top left corner, going down by 1 and keep going to the right side. Okay, so it looks good. Now I want to replace this number as a current point number. So you can do that by using a sort. By referring to the attribute sort that I've just created. Now the current point number will become something like this. Okay, this is necessary in order to use the code that I wrote previously. I didn't want it to make it change because I might going to get some bug because of changing some code. So I'm gonna keep it like this. Okay, well, I'm wondering if the view is okay. It looks pretty blurry in my preview. Not sure if it's running all fine, but hopefully it is. Is it running really slow right now? Hopefully not. Well, let me see. Well, I think I am connected to the Ethernet, so should be fast enough, hopefully. Well, let me know if you see any latencies or something. Okay, so I have now sorted the point. Next thing I would like to do is to apply some initial attributes in order to use for the simulations. Okay, so let's give several attributes. First of all, u value, which is a x directional velocity. Let's start with the 0. V value, which is going to be the y directional velocity. And P, which is going to be used as a pressure, which is not really necessary, but might be good to have for visualization. A M stands for the mass, I think, which is going to be used to determine if there is any obstacles or not. For default value, I'm gonna make it as 1. Okay. Also, I'm going to create an attribute called O, which also going to determine if there's going to be an obstacle ball in there, which is a bit similar to M, but this is more constant value. Okay, so the important value is going to be these U, V, and M. P and O are optional. It's not really necessary for the simulations. Now, the other attributes that I need is the one called S, where it determines which part is going to be used for the simulations in this grid. Now, which also determines the wall. Okay, if the S is equal to 1, that point can be used for simulations. That point can be used for flow. If the value S is equal to 0, then that part is going to be a wall and it's not going to be used for the simulations. So what I would like to set as a initial setup in terms of the wall, it's going to be something, it's going to look something like this. So if I draw it, I want to make a wall like this and give an initial velocity in this direction, somewhere around here, maybe using the whole grid on the left hand side, going this way. And because there's a walls on the back side and the top and the bottom, the velocity always have to go through the tunnel and have to leave from the right hand side. So you're always going to see the flow going right side like this. Okay, and in order to determine if this is a wall or not, you can use the value S for that. So if Ix is more than 0 and Iy is less than, more than 0, and if Iy is less than num y minus 1, then you can set the S to 1, otherwise set it to 0. So 0 means it's going to be blocked and not going to use for the simulations. Now let's check this out. let's check the S value. Okay, so everything inside the grid is 1, but on the border you have 0. But on the right hand side it's opened. Okay, so this is the initial conditions for the simulation. I mean, you could customize these afterwards, but let's try with these setup for now, because the visual is pretty nice with this setup. Okay, now what else? So I guess that's all for the point. Now let's also create some attributes for the detail as well. Okay, so I'm going to create another attribute wrangle. This time I'm going to set it to detail and set some additional attributes to the detail attribute. First of all, I'm going to set the attribute called density, which is going to be used to calculate the pressure value on each point, which is not that important, but might be good to have. Another one, I'm gonna create a value called numx, which is going to be used to determine the number of points on the x directions. So let's which is equal to the column number. So let's copy that value, as well as the num_y, which is the row number. And let's also get the number of cells, which is just a multiplication of numx and num_y. Let's also calculate the size of each cell, like the height and width. And I'm gonna call this as h. And that will be number of x values divided by width, I think. So number of x divided by width. Now I don't have the width yet, so let's also bring up the width value. Okay. What else? Now the important attribute is these numx and num_y and number of cells. These parts are kind of optional if you need to calculate pressures and stuff. So it's not, to me it's pretty optional. I'm also going to create a per time frame per second value, which is coming from the JavaScript implementation, but I found out this might not really be necessary. Now another important value that you need to have is number of iterations for the optimization part, which is the OpenCL part. More numbers you iterate, more precise or more correct results you get. Okay, and that's about it, I guess. I mean, you could also have additional gravity, which in this case might not be necessary, but let's go with 0 for this one. Okay, so these are for the detail, and let's copy these value. What's num? Okay, should call this num iterations. Okay, let's copy all these values from here. So width, coming here, number of x, and number of y. For the density and number of iterations, I'm gonna copy that parameter to the controller. Let's drag and drop these parameters here so that I can access it later. Let's call the density maximum number of density to 1000, the number of iterations to 200 maximum. Okay. So for the density, I'm gonna go try with the 100 first, and not for the number of iterations. Let's call this 50 for initial test. Okay, so for the initial attribute setup, I think that's pretty much it. Now it's time for me to go further. Set a initial u value, a velocity value, as well as a obstacle and point for the smoke source. Okay, so you have 3 informations to add to this. So for the initial u value, in the example that I showed you previously, I have just set the u value for the left hand side point to be equal to somewhere around 1 or 2, so that it goes to the right hand directions. So let's create that value first. Gonna create a point, another point wrangle, and let's call this init velocity. And you could use some additional geometry for a guide to pick where to set the velocity, I guess. So shall we do that? For example, you could create a guide grid. Let's make these and change the size to something really big on the y directions. Maybe that's too big. A bit thinner on the x directions, and move this grid so that it covers several points on the left hand side grid, like that, to capture the points where you set the initial velocity. Okay, so let's call this. First of all, let's see the distance between the grid and each point. I'm gonna use the XYZ distance, and if the distance is small, close to 0, then set the initial u value, which is going to be the x directional value, x velocity value, to 1. Let's give it as a parameter. Let's call this 1. And let's copy this value to the parameter. Like that. Okay. Let's also check which point has been picked for the initial velocity. I'm going to set the color to red to check. Now nothing is changing, so maybe I'm doing something wrong here. Maybe the grid is not okay. The y value of the grid is not in 0. Alright, so do it. Okay, So that's for the initial velocity. Now let's also set the initial point for a smoke source or a colored ink source and the obstacle. Okay, so let's give another point wrangle called init source. All right. Now actually, if you want to do this in animation, if you want to change the source positions and the obstacle positions in animation, you have to do this inside the solver. If you're okay on the static positions, then you can do this outside the solver, but if you want to do it inside, if you want to use it as an animation, this is not the place you do. So maybe I can skip it. But instead, I can still create the position for the sources and the obstacles. So let's create two add point node, one for the source, one for the obstacles. Okay. So for the source, I'm going to create, let's say, 3 points and bring the point to the left-hand side corner, since this is where the velocity starts, and use those as sources for the smoke or colored ink, and let the smoke go to the right hand direction using the initial U value. Okay. Let's also set some radius for each point. So for that, I'm going to use a attribute create to change the radius for each point in the same value. Let's call this radius, and let's have another parameter to change the source radius. Okay, as well as let's move this here, as well as a obstacle radius. All right, so each one I'm going to set the value from 0 to 10. Let's copy the source radius and paste it to the value for the radius attribute. For the obstacles, I'm going to use the same radius attributes, but with a different value set it here. Okay, paste relative reference. Okay. All right, and for the obstacles, I'm gonna try with 2. Then maybe later I can change it to any number of points. Okay, so somewhere around here. Okay, so let's say these are the obstacle point position, which is going to be used as a ball to make it simple. And these are the points for the sources where it starts smoking. Okay, so we have 2 informations here. Now, I think I am ready to do the simulation, start doing the simulations at this point. So let's do this, shall we? Now, I'm going to include all the sources, obstacles, and the grid points together. So what I'm going to do is to make a group for each object. This one, I'm going to call this grid. For a point group, this one, I'm going to call this as a source. For this one, let's call this obstacle. Right. Now for the grid, it is going to be slower if you have a plain informations, like a face informations. So I'm just going to keep the point and delete the faces at this point to make the simulations faster. So currently I only have points, and which also have the detail attributes, so that's fine. I don't really need the face informations for this. Okay, so now I think I have necessary information, so I'm going to merge all these together. And going into the solver. Alright, now as a guide, since I might want to animate the sources or the obstacles outside the solver, I'm going to connect these points to the second and third input as well. Alright, so that's the initial setup outside the solver. And from now on, everything is going to be done inside the solver. Okay, let's do that. So, let's recall a method. How are we going to do the simulations? Okay, so first of all, what we need to do is, first of all, let's give some diagram here. First thing I would like to do is to update the obstacles. Right. Now, also update the source. Position, which might going to be animated. Okay. Now, next, if you have a gravity, you will need to have a integrate method, but in this case we don't really have using gravity, so maybe we can skip it or add this later. Next, next thing you could do is to calculate the divergence, just as you saw in the last PDF, and optimize it to balance between the inflow and outflow. So okay, and this part, which can be used either VEX or OpenCL. Hey, this is the main part, I guess. Now next, after you have calculated the best value for the UMV for each grid to have the most balanced value in terms of the divergence, next you could advect the velocity and the smoke, meaning update the velocity and smoke value. Velocity value is either U and V, smoke value is M. Okay, and as an addition, you could also update pressures within the optimization part. if you want. Okay, and after you have updated the velocity, you can go back to the next frame. Okay, so that's my plan. Let's do this. Right. So let's start by splitting the point into the grid and the balls and the obstacles. The grid and source and obstacles, I mean. So first of all, I'm going to get the source and obstacle points, split it. Okay, so this one is the source point, which might going to be updated in terms of the positions, and this is the obstacle, which as well might going to be updated from the input 2 and input 3. Okay, so this one is related to the source, this one is related to the obstacle. Now, first thing first, let's update these positions using these second and third input. Okay, so I'm gonna do point wrangle. Connect this to input 2. Let's color this to red. And what I want to do here is to just update the current point position with the input coming from the second input. Position coming from the second input. And do the same for the obstacle. This time using this part, this input. So update source boss, update obstacle position. Now for the obstacle, you could also calculate the moving velocity for the obstacle so that you can also manually change the vector field by moving the obstacle, which is pretty cool, I think. So let's also calculate how much it moved from the previous frame to the next frame and use that as a velocity value to add it to the current velocity field. Okay, so let's try to do that. So I am going to create an attribute called pause and use this one to store it as a variable. And if the frame is equal to 1, I think there are no velocity yet being created for the obstacle, so let's call the obstacle velocity to 0. Else, I'm going to create an obstacle velocity by subtracting the new obstacle position by the current point position, which should create some velocity value, how much it has been moved. Okay, now update the position. Okay, and now that I have this value, I want to add this value to a u value, u and v value. to update the current vector field. Okay, so let's do that. So the current vector field is this one, grid. Current point is this one, which has all the informations, U and V and M and all the other attributes. Now I'm going to manipulate some of the attributes based on this information and this information. Okay. First of all, let's reset the source for the grid. Right. Now, what I'm going to do is since each point has each obstacles and source point has a radius attribute, I think, this one. So, I'm going to use that value to search for the point, whether the grid point is within that radius. And if that's so, I'm going to use that grid point as a new source point. Right. So to do that, I'm going to say if. Now, first of all, I also need some conditions here. It's better not doing anything on the border when you do the simulations, because the border has some special conditions. So you always want to do the simulations within, except the border, but within just one step inside the border. So I'm going to make that condition first. If x is more than 0 and x is less than detail num x minus 1 and y is 0 and y is less than detail 0 num y. So this conditions is pretty crucial. You need to have this, otherwise it's gonna broke in many places. So you're gonna have to be careful. Let me just check if I have the right value. Now I have, somehow the h value is wrong. I have some weird value called numx with lowercase, so I think I need to fix that. Gravity 0 is fine. Okay, let's check the h and numx. Okay, so here, yeah, this already has some problem. This has to be numx. Seems like I need to rename this. Okay. Okay, so numx still have some problem here. Numx. Okay, this one. All right. Now that looks fine. In terms of the h, that's also correct. Okay. Going back to where I was. So I was updating the source. So in order to find out the source, I'm going to first use a new point function to search for the closest source point for each grid point. Get the point position. And calculate the distance between the current point position and the new position. If the distance is, now I think I need to have the radius as well. If the distance is less than the radius, then you could use that grid point as a source point. Let's check with the color first. I'm gonna call this green, see where it is. Okay, so here it is on the corner. Looks a bit small. Maybe I can make it bigger later, but looks fine. Okay, so I got the point, I got the positions. Now what I want to do here is to set a smoking value to 0. Okay. And initially all the value on the other position is equal to 1. But for the sources, I'm going to make it to 0. Okay, which is going to be pushed to the right hand side to be mixed with the value 1 for all the other positions. Okay, so that's that for the sources. Maybe I can increase the radius a little bit bigger, going back to the controller and increase the source radius, yeah, just like that. Okay. Next, let's also update the obstacles. I'm going to use another point wrangle. Call this update obstacle. In this case, I'm going to use this value here. Right? Now, there are two informations that I need to refer to. One is the obstacle positions and obstacle velocity. Okay, so let's get those two values. Right, so just as I did to the update source, I'm going to look for the nearest point from the second input. Get the point position. Right, then get the radius just as I did with the sources. What else? Now let's give a same conditions as I did here. Let's copy this conditional and give it here. I think I have some, okay, so this is a new point. Alright, so within this conditions, I mean, maybe I can write this here. Within this condition, I'm going to again calculate the distance between the current point position and the new position, the obstacle positions. If the distance is smaller than the radius again, then I'm gonna set the property for attributes for the obstacle. First of all, the S has to be 0, just as those blocked walls on the border, left top and bottom border. Okay, and for the M value, it could be 1, fixed to 1. The U value, on U and V value, actually for these one can be referred to the current velocity from the obstacle. So you can use a point, get the now actually what I have as an attribute is called obstacle velocity, and it's a vector value. Okay, so I think that was something like that, right? Okay, it is. So we need to split it into a x component and z component. Okay, so actually the u is obstacle velocity dot x, and v is obstacle velocity of z value, since this is a xz plane. Okay, and yeah. And you also might want to update the next point since as I said, as the PDF says, if you are working on a grid, okay, on a grid, actually what we are looking at is this point when we say at P or at Y or something like that. But in terms of at U and at V, at U value is not actually the value right here. It's not this position, but it's actually at this position. This is at U. So you also need to update at U plus 1 right here as well. If you are updating at V, you might also want to update at V plus 1. I mean, yeah, at B, not B plus 1, but the next V value has to be updated as well for each point. That's kind of a role of at U and at V here. It's a bit confusing because I'm using the same at value, but you have to virtually think that the position is half point offsetted. Okay, well, I guess you don't really need to be that strict, but you do need to have this information when you do the optimization for the divergence. All right. So in this case, I'm just updating the left-hand side value and top side value, U and V. So that might not really be enough, but so if you want to do it more precisely, you can also update the one next to the current point, which is I at x plus 1 plus num y plus I at y. So you have offset it in the x direction by 1 in this case, and update it with the same obs vel.x. Do the same for the v value. This line is, I think it's optional, but if you want to make it, if you want to simulate it precisely, I think you do need this line. So let's do that. For the v value, you want to add y by 1. and update it with the obstacle obstacle velocity z. Okay, and finally I'm gonna set the O value to 1. Okay, otherwise the O value should be equal to 0. Which determine if it's an obstacle or not. Which is pretty much an optional value. I'm just going to use this to color the point later. So not that important. These part are the important part. Okay. Okay, hopefully that is working. Let me check. Let's color this. See if I'm getting the right point position. Let's make it blue. Alright, so I have 2 obstacle points. Each point is going to have these value set. Okay, alright. Now I have set the sources and obstacles. It's time I do the optimization using Gauss-Seidel method, which is the most heavyweight part. Okay, so just as I said, I'm going to try to create a prototype using VEX, then try to re-implement that in OpenCL to make it a bit faster. So where do I start? Let's look back at the PDF that we were looking at. So what we need to do is here. So we need to force the incompressibility. So if the balance is not correct in terms of the inflow and outflow, we need to fix it. We need to balance it so that the direction, the total amount of inflow and overflow will be equal to 0. Okay. And in order to do that, we need to calculate the, we need to update the divergence, this value here. For each point is the center point, and for each point you have the u and u plus 1 on the x direction, and you have v and v plus 1. Okay. And for combining these values, you're going to have these equations to calculate the divergence. And in order to optimize it, you need to update each u and u plus 1 by these value here. And do the same for all the other cells simultaneously. So in order to do this simultaneously, you need to do a little trick if you want to do a multi-threaded way. If it's not a multi-threaded way, you have to do one by one, like a simultaneous linear equations. Okay, but if you want to use it multi-threaded way, there is some way to do that. And you also need to also care about if the point is at the border or not. If it's at the border, you need to ignore that border inflow or outflow. Remove that, so that the average value is going to be something different. Okay, so this is the general case. And for each grid point, you need to solve that one by one, because once you solve the one grid, if you have a grid like this, you could only solve this grid by solving the next one, and you can only solve this grid by solving the previous one. So you need to do one by one in order to solve the grid. So that's a bit time consuming, because you have to loop through all the grid one by one. So if you gonna do this on VEX, it's gonna be so slow. But actually there is a way to make this multi-threaded way as a trick. What you can do is to split this grid into a checker mark pattern. One looks like this. One looks like this. In this case, first of all, you can solve this part simultaneously for each checker pattern part. Then after you have solved these part, you can use the updated value on each cell to be used on the other checker pattern. In this case, it seems like you can do the multi-threaded way. Multi-thread, calculate this one, then multi-thread, calculate this one, and going back to the other one, like that. Which is called as, I think it was called as odd, even, Gauss-Seidel method, I think, which is not listed in this PDF because the sample in this JavaScript is just falsely doing the old-fashioned way, more slower way. But since VEX can do the shader-like multi-threaded calculations, we're going to use this odd, even Gauss-Seidel method instead. Okay, so let's try to implement these part. First of all, using VEX. Okay, and last, the another thing you need to do is to run this optimization, like linear equations, multiple times to make the best result, like 100 times, 50 times. This is where you use the value that I set, number of iterations. Where is it? This one. Okay, so more number you have, more precise value you get, but slower it gets. Okay, so I'm gonna use the what was that I'm gonna, okay, so I'm gonna use a point wrangle to do the, so for the VEX way I'm going to use the point wrangle together with the for each loop. Now what I need to have is 2 point wrangle, one for the odd number Gauss-Seidel, not sure about the spelling, and this is for the even Gauss-Seidel. It's also called as black and red Gauss-Seidel, I think. Okay, and most of the code is going to be shared. Just the calculation point is just different. One is on the even grid, one is on the odd grid, odd checker grid, and one is on the even checker grid. So for each point wrangle, I'm going to pick one of the checker pattern. Like if I'm going to start with here, this one, this one, this one, this one, this one, this one. You can get the condition pretty easily by just adding x value and y value and calculate the modulus, and if let's and see if it's even number or odd number. So if it's odd number, let's test by coloring it by 110 yellow. It's a bit hard to see it with the red. So as you can see, you are having a checker mark here. If you make this condition to 0, an even number, the checker pattern flips. So 1 will go for this conditions, and another point wrangle goes with the other checker point conditions. Okay, so that's how you can go. That's how you can do the multi-threaded Gauss-Seidel optimization. Okay, so let's get into the detail. Let's forget about the pressure for now and only focusing on the velocity. Okay, so first thing first, I'm going to get the number y, how many points on the y directions. Okay, and so what I am going to do now is, let me see. So I'm going to check if the point that I'm looking at right now has a border or not. Okay, so let's see if I'm looking at this point right here and looking at each side and check if there's a border. If the s is equal to 0, that's a border point. So in this case, these point and these point are on the border, so this will be 0. So in case of these point, you have 1, 2, 3 free spaces, but 1 wall. So if you add the s value, the total value is equal to 3. For this point, you have this value is on the corner, so s value, the total sum of the s value is 2. For the point right here, it's 4, and so on, which corresponds to where I'm calculating the number of borders here. Okay, so let's do that first. Okay, so let's check the current s. Let's get the s on the left, right, top, and corner. S x 0 point is 0s. Current x minus 1 multiplied by num y plus I y. Okay, do pretty much the same things for all the 4 corners. X1 is just making this part plus 1. For y, make this one minus and this one plus. Rename it to, okay, this one 0 and some y. Okay, and the total amount will be adding all these values together. Oops. Okay, let's check that value. See if I'm getting the right value here for each point. Okay, so I have named it SS. So there's 4. There's 3, 2, and 1. Where is these 1 value? Not really sure. Maybe it's where the, let's check where this one go is. I know these are for the borders, I think, but for these one, not sure where that is. Okay, if s is equal to 1, color it to Blue or cyan. See, check. Okay, seems like it's on the border. Okay. I thought I have made the conditions to accept. Wait a minute. I didn't create the conditions to ignore the border point, so I have to add that. Forgot about that. So, which is same as these conditions here. So let's copy these and paste it here. Okay. Now I think there are no more SS value equal to 1, so the minimum is 2. Okay, looks fine. So 2 are the one that's on the corner, and you have 3 and 4, and 0 is on the border. Okay, looks fine. Alright. Need to check this for each step, since this is each step is pretty tricky to check. Since once you run simulations, and if it doesn't work, then you don't know where it's wrong in terms of implementation. It happened to me a lot, so I needed to do that. And since, well, if the S value is border, S value is equal to 0, then, which means it's on the border, so we can kind of skip the calculation. So I'm going to call this return, in this case. Okay, now, next step is to calculate the U and V value for each point in order to calculate the divergence. So let's look this from the top view. What I mean by U and V is for each point seeing it as a grid, and for this point you have at U value right here, and there's another U value for the next point here, but let's call this U plus 1, and you have at V here and at V plus 1 right here. So for each point you want to calculate the divergence using these 4 values, and if the balance is not well, then you have to fix that. You have to optimize that. That's what you need to do. So let's get those 4 informations. Let's call U0 is you can just get the current U. U1 is the one next to it, so 0.0 U ix plus 1 multiply by num y plus I y. So V0 is the current V. The V1 is the next V value, which again use these function. So V y plus 1. Okay. So now you have 4 values. It's time you calculate the divergence, which is this value here. The next U value minus the current U, the next V value minus V. So U1 minus U0 plus V1 minus V0, right? And this is where you're also going to use so-called technique called over relaxation to make the simulation faster. the optimization faster, which is explained here. By multiplying these divergence with a constant value from 1 to 2, you can make the simulation faster somehow. And it says it's using 9.1 in this case, so I'm going to use the same value, 1.9. Okay, so the divergence is E multiplied by 1.9. Also, you need to divide these by S value, just as listed here, which in this case could be 4, could be 3, or could be 2. So let's divide that by S as well. All right. So let's see if I'm doing this correctly. Yeah, I think so. Okay, so actually this is the divergence, so I shouldn't write it like this, but let's call this P. E multiplied by 1.9 divided by S. So this is actually a pressure value, actually. So you could kind of use this as a pressure. Okay, but which is I think listed here, but you need to also have a density, a grid spacing, and time step to precisely calculate the density. So if you want to have the computed density, you first need to calculate the density. Wait a minute. The density is on the detail, wasn't it? Yeah, the density on the detail, so what was I? Density multiplied by the H value divided by the time step. And I think I can leave it here or here. And the actual pressure is P multiplied by this CP. We can also visualize this later to see how it looks like. But the important thing is this processed or optimized divergence value. So what I need to do is to update the U and V value based on this P value. Okay, so let's do that. What I'm gonna do, this is more of a difference. This is more of a difference of U or V value. This is to organize or tweak the current U or V value to make it make the inflow and outflow balanced for each cell. So in order to use this to update the U value and V value, you need to re-update the current U in this case, this is x multiplied by num y plus I y, which is equal to pt num, so you can just use pt num, but I think in this case it's easier to see with these point numbers, so I'm gonna keep it like this. And multiply sx0 plus p, which is gonna be added to the current u to tweak the value. Okay, do the same thing for the next u and the v and the next v to optimize each value. And one iteration is not enough. You have to run this multiple times in order to make sense. Okay, so for the next one, it's gonna be like that. This one is sy0, this one's sy1. This one +1. Okay, I think that'll do it. So you need to have this add option to make sure that this adding these value to the current u value. Oops. Okay. So now that I've done this, I am just copying the whole code that I have here. And paste it to, wait a minute, I'm just gonna copy everything here and paste it to the next point wrangle, but just change this condition to make it work on the even number. So originally it shouldn't, it wasn't, and it wasn't possible to run this simultaneously like multi-threaded, but by split it into odd number and even number checker mark, you could actually use it with the point wrangle multi-threaded way. So that's one thing, it's pretty good. But downside is that one iterations for this step is not enough, so you need to have several iterations to get the best result. Okay, so I'm going to use the for each loop with the feedback options like this, and the number of iterations has been determined here. Copy that and use that for the number of iterations here. All right. And that should solve the UMV inflow and outflow balance. Hopefully. We'll see that later. Now, now that we have these, it's time we update the velocity UMV and move the velocity to the next directions. Also the smoke as well. Alright, so let's do that. What I'm gonna do is create another point wrangle. Now in order to update the velocity and smoke value, M value, the plan that I'm gonna do is for each point I'm gonna check the current U value and V value. Okay. Since each point, let's zoom in. Oops, what's happening? What? Okay, so for each point, let's just make the top view. So what I'm gonna do, each point stand as a grid. Okay, and each point has the U on the left hand side, U plus 1 on the right hand side, B on the top, B plus 1 on the bottom. And using these U and V values, I want to move this point based on this U and U plus 1, V and B plus 1. Could be in this direction, could be in this direction. Let's say it's this directions, right? Okay. And right here, what I'm gonna do is to sample the new U and V value. I'm going to check for the new U and V at this point position, at this point, which is going to be sampled from all the around the points, all the surrounding points. Get the average, calculating the weight with the distance and so on, and update the current U with this one. Okay, same for the M value. For each point, actually not the positive U directions but negative U directions. So originally the U V direction goes here, but you go into the negative direction to sample, to move this point, so that it will go somewhere in this direction or this direction. Same one for these. Sample the one that's on the negative UV directions, sample the M value, and update it to the current one. Okay. So that's the advection. That's what I am going to do now. So let's do that. I'm gonna make it simple using the point wrangle function, I mean VEX functions, to do this, rather than walking on a bunch of arrays in a difficult way. So let's make it simple. I am going to okay. So the function that I'm going to use is PC open and PC filter to get the average value in specific direction, specific positions. So first thing first, I'm going to what I need to do is to get the sample position, which is the current point position minus set f at u, f at v. This is, I'm making it too simple, but this is the basic idea. You're going to move the current point position to a minus direction of the current uv. You kind of also need to consider the u plus 1 direction and u plus v directions, but let's make it simple to test for now. Now, so this is the sample position. Now let's use this with the PC open. Int handle is equal to PC open 0. Use the p attribute with the sample position. You also need to set the radius. Set the radius to big enough value and limit the number of points to be searched for maybe 9 is enough, I think, since wherever you go, these points, let's say the sampling point is somewhere around here, you have a big radius right here. If you have at least 9 points, I think that'll be enough to do the sampling. Right? If it's just 4, might not be enough. Might going to have these points. Might not be enough, so I think you need to have at least 6 to 9 point. So this example, I'm gonna keep it to 9 for now. Smaller the low res result you get, but higher the calculation cost is going to be higher as well. So you need to seek for the balance. Now that I have opened the PC point cloud, let's get U, V, and M value based on this handle with the PC filter. So I also need to set the conditions. If at S is not 0, which means it's not on the border, is the first condition that I need for everything. The other condition will be, let's see, let's see, what will be the other condition? I also might need to check whether the point, well, let's just check with this condition if it's gonna work. I think I also need to I think I also need to check other conditions for this one, but this might be okay. Let me just check. So if it's like this, then let's create a new variable called new U, copying the current U, float new V, copying the current V, new M, copying the current M smoke value. And if S is not equal to 0, then new U is PC filter handle U. New V is PC filter handle V. New M is PC filter handle M. And outside a condition, you can now update the U, V, and M. Okay. Hopefully this works, and this is Advection. Okay. Now, I might also need to do one more things, which is called extrapolate, which is to copy the U and V value, which is on the border, to the the next point. I think this was also necessary, so let me just add that, which is pretty much the same things as the JavaScript demo code was doing. Extrapolate. Okay, so if I and y is equal to 0, which means I guess it's on the border, you copy the U value from the current point number +1, meaning copying from the next y value. Okay. And if y is equal to detail num y minus 1, then in this case copy the u value from the top value. So in this case minus 2, I think. Let's have this num y as a variable. And do the same thing for all the x, all the v value. So if x is equal to 0, f at v is equal to 0.0 v ptnum plus num y, which is the next column. If x is on the end, meaning num x minus 1, then copy the point of v by multiply by 2. Now this part, I'm not really sure what it's doing. It's just copying the u and v value from the copying the value if it's on the border, then just copying the value from the point right here to the border. So I'm not sure if it means anything, but let's see. And you have advection. I think that's it for the simulations. Now is the time to check if the simulation is running correctly or not. So the best way to check if the simulation is working is to color the m value, the smoke value. So let's check by coloring the m. Now already it looks something weird, so maybe that's wrong. Okay, I think it's wrong. Let's try to show the m value. Let's see where it's wrong. So obviously something must be really really wrong here. Did I make it feedback loop? Feedback age iterations, feedback, okay. So let's check one by one to see which part is wrong. So seems like the advection part might be the place it's doing a bad thing. Okay, so if I play it, yeah. So I'm guessing this part must be something wrong. Alright, let's check. So first thing first, the conditions. Conditions is always pretty critical. So okay, so x is more than 0. X is less than the border. So okay, this looks correct. Okay, and we have this condition. This was correct as well. Now and we have checked this value as well, so that I think that's correct as well. Now this part, maybe, I'm not really sure. Okay, so let's check these part. So first of all, the place where I calculated the diversion, let's check that. Let's also check if this is odd and even. Okay, right. Let me also check the previous implementations I did, if I did something wrong. Right, should be correct. Okay, now let's just go with the first iterations and see how m value changes, or s value change. No, the u value changes. Let's check the u and v as well. So if I'm doing correctly, the u value has to go from left to right with several iterations. First of all the values on the left hand side had u more than 0, and all the other positions have u equal to 0. But over time, with this optimization, the u value transferred to the right directions, and you have to have some balance between all the positions. If that's not happening, then there must be something wrong. For the v value, there are currently no vertical initial directions, so it's hard to use this as a checking value. So for now, just visualize the these value. So let's try to increase iterations. So 0. First thing to check is the units. Okay, so suddenly I can see that suddenly the value is going crazily high, which is totally wrong. So the implementation, okay, so I also see these none value, which is wrong. It has to be within close to 1. The value should be close to 1 somehow. So these are all wrong. Need to fix that. Need to fix some place must be wrong here. Let's check where that is. It happened a lot of time when I first implement this, and it was mostly on the conditions. So I thought it was on the conditions. Let's check if I have x value, y value. Okay, that's fine. Num x, num y, if I'm getting it correctly. That's also important. Okay, let's replace and num y. Num x, this is num y. Okay, let's make this bigger iterations. All right, and this part is not really important here. So we have s, we have calculated. So Must be wrong with somewhere around here, I feel like. So for this one, maybe instead of just getting the current U with this command, with this attribute access, let's try with accessing with the ix multiplied by num y plus I y 0.0 v ix multiplied by num y plus I at y. If that, oh, something changed. That's weird. That's weird. Huh. Why is it? Okay. Let's change this to this part as well. If that's gonna fix it. Well, it did change the value, but it's still really big, so still wrong. Okay. Okay. Let's see. So I want to check this divergence value. Okay, it's pretty big. First iterations. Huh. It's all -1. That's weird. I want to reuse the whole code except for this part, so I'm going to make it this a parameter. Okay, and I'm just gonna copy all the code here, expression, paste it here. But I'm going to create a integer, the same integer parameter called odd even. Oops. And this one for 0, this one for 1. Let's call this is call for 1, this is call for 0. Okay. Okay, now what I want to check is each U0 U1, V1, and 0 and V1. FU0, okay. FU1, all right. FV1, 0. Okay. FV1. Okay, so for the initial value looks correct. If I increase this a little bit. B looks a little bit bigger. U still in the good range. If I increase this to 100, just burst. It should not go this big. So something is still wrong here. Okay, where is it? Where is it? Ah, I think I know where that is. I think I need to make this p negative. No? No. Nope. I thought that was it. It's not. Everything goes still whole different. But the previous code that I wrote is something like this, so code-wise, I think it is correct. Can I just try copy and paste the whole code and see if it's gonna work, just to check? Let me do that. Okay, so from here, let me try replacing like this. In this case, n is equal to num_y, so okay, now it looks correct, so I must done something wrong in terms of the implementation. Okay, let me go back. Okay, where did I do wrong? Let me go from top to down by looking at the previous code. Okay, so first of all, CP is not really important. Sx0 multiplied by num_y, ix. Adding all these, checking, okay, should be fine. For this one, u0 is ix multiplied by number y, u1, ix plus 1 multiplied by num_y plus iy, v0 is equal to oh, this is x. Okay, this might be it. Nope, still not. Okay, but there must be some careless issues somewhere like that. Okay, so v0 is ix multiplied by num_y. Okay, and this one is, it's fine. B1 is adding y plus 1, so looks correct. u1 minus u0 plus uv, v1 minus v0. Okay. And p is minus divergence divided by s multiplied by 1.9. Okay. Then updating ix plus multiply by num_y. Okay, minus a, oh, okay, this is not negative, this is not negative. Okay, there you go. Sorry for that. Now the number is not overflowing anymore, it looks balanced. I think it should have been fixed now. Let's check again. Now let's increase the, let's set the iterations to somewhere 50 and see how it goes. Okay, the smoke. Well, just disappeared. Maybe there's still something wrong here. It's seems like it's missing why am I showing this S? Seems like it's missing the source updates. The source is not being updated correctly. Some reasons. Okay. Now, for each frame, I need to also bring the obstacles and sources back into the output. So what I forgot to do is to merge these source and obstacle points back into this right here. And I think I need to feed in the updated position value here. Alright, like that. Okay, so let's see how that goes. So that the source is, and that's not gonna disappear. Alright, finally. Okay, I think it's working. Let's try to increase the frames and move the sources to see if it's really move the obstacle to see if it's really working. Let me increase the source radius a little bit and check. Okay, so let's move this. Alright, so yeah, I think it's moving. I think it's working. Now something looks weird. Something looks wrong here. I still have some problem here, I think. Maybe the obstacle value is not being updated correctly. Seems to have, it uses all the trails as the obstacle, which is pretty much wrong. Let's see why. Okay, this is wrong. I don't want to keep the trail. Need to re-update it. So should be somewhere around here. Update obstacle. So let's see. Actually, I need to reset the S value to 1 each time I update the obstacles. I think that's what I needed to do. What about the source? Do I need to update anything? Maybe not. Let's check this again. Okay, trying to move the obstacle. Okay, there you go. Looks much better. Okay, I think it's working. Alright, so for now it looks okay. Even with the VEX, with this number of points, it looks fine in terms of the speed. Currently this is just a point, so let's use the previous geometry, I mean the grid, somewhere around here, to recolor this grid with the this point. I'm going to check, copy the color. So that it could now run on the grid. Okay. Now let's keep this on the center, just like an example. And let's make the sources a little bit bigger in terms of the radius. See if we're going to have some interesting movement. Not so much. Not so much. Let me increase the obstacle radius as well. And for testing, let's keep the number of sources to 1. Make it bigger, and obstacle to 1 as well. Okay, yeah, I do see some flows here. Thing is that the resolution is a bit low, so it's a bit hard to see the detail here. So what I want to do next is to increase the detail. Now I could also increase the flow, the initial velocity, to see the difference. Let's say if I increase this to 2 to make it faster. Now I see more interesting flow here. Okay, so let's see if I increase the detail, what would happen. Currently it's 128 by 64. So if I double this, 256 by 128. So it still runs, but start to become a bit slower. So the next thing I want to do here is to make the simulation faster by re-implementing the advection part. No, not the advection, but the where was I? The projection part with the OpenCL. So let's do that, shall we? Obstacle radius is not changing, is it? It's not changing real time. Well, let's make it faster then. So going back to the subsolver, this is the part which is taking the most of the time to calculate. If you check the performance, you can see that the even Gauss-Seidel and odd Gauss-Seidel part is taking the most time. This part, because it's inside a loop for each loop, and we don't want to use that. So instead of using this, let's use OpenCL instead. And because the calculation done here is pretty simple, I mean pretty straightforward, nothing uses the VEX functions just a set point attribute, which is doable in OpenCL, or point, which is also doable. Just getting the attributes and feeding the value in the attribute, and just those conditions, which are all possible in OpenCL. So it's pretty easy. I think it's pretty easy to re-implement in OpenCL. Not much, since I'm not using much VEX functions here. So let's do that. Don't forget to save your project, because OpenCL might kill your project. Let's create a switch to switch between OpenCL and VEX. Now, first thing you need to do in order to use the OpenCL to define which attributes you want to access to. Okay. By going into the binding, you're going to define every attribute you want to access, read or write. So there's going to be 11 attributes. First one, this is going to be attribute. First of all, the x, integer value x for the point. Readable is fine. Next one is y, integer attributes for the point. Readable is fine. Next, a s value for that point attribute, float. Readable is fine. I'm not gonna update the s value. Next one, u, float. Nope. The attribute for the point, float. This is going to be updated, so you need to check writable. Oops, I forgot to write here. Okay, so x, y, s, and u. Next one is v. Float, no, not attribute. V, point, float, writable. Next, e, num x, number of columns, which is in a detail attribute, integer. Num x, readable is fine. Num y, attributes, detail, integer. Num y, readable is fine. Next, if you want to calculate the pressure, then density, which is detail. Float, was it? Float, readable is fine. Okay. As well as h, float, no, detail attribute, h, detail, float, readable. Time step, float, no, attribute, detail, float, readable. And finally, pressure, p, attribute, p, detail, no, point, float, readable, and writable. Okay, it's a lot, but now I have binded. You can now use these attributes inside the kernel. Now, because I have two steps, one for the odd, one for the even, I also need to do the same things on OpenCL. To do that, you could use an option called not here. In order to use the two code to run simultaneously back and forth, you could use this write back kernel option. It's pretty handy. Could do the exact same thing that I did here with one node. Now to use the write back kernel, you need to write a kernel section inside the code right here, calling write back. And what you just need to do is to do the even number operations here and odd number iterations here, and just that. Okay, so let's try to write this function. Okay, I'm going to open this as a guide. To write it in the OpenCL. So left hand side we have VEX. We want to translate it into a OpenCL. Okay, so first of all, these conditions. If at x is more than 0 and at x is less than at num x minus 1 and at y is more than 0 and at y less than num y minus 1. Okay, another conditions, if at x plus at y modulus 2 equal to 0. First of all, I can calculate the density. Float CP is equal to at density multiplied by h divided by dt. Okay, and float s well, first of all, float s is equal to at s, float sx0 is at s, so the point function is related to get at. Okay, and we can just use x minus 1 multiplied by at num y plus at y. Okay, float s x1 at s dot get at x plus 1 multiplied by num y plus at. Okay, well, let me just copy all these. Okay, then I'm gonna replace here with at s dot get at. You cannot use I at. Okay, do the same thing for this one, at s dot get at. Okay, and s is equal like this. Now it's a bit this is not safe. I mean, this is not fail safe. I think it might be better just checking with the small number like that, which is pretty much the same meaning but a bit safer, I think. Okay, should do the same thing for here as well. Okay, next u value. Point, so this one u at u get at this position, at u get at, let's just copy these. No, this is v at get at. Okay, v. All right. Now calculate the diversions and blah blah blah. Okay, copy all these. This must be fine. This must be fine. This is not fine. To set the attribute, you have to do p dot set and current p plus. Okay. Wait a minute. I think I needed to add these like this. Yeah, forgot to do that. Okay, for this one, I'm updating the u value, so set at x. Okay, I shouldn't use I here. Forgot to delete that. Okay, and x0p. Now I cannot use add options, so I need to get the current u value and add it to here. So that is at u dot get at x multiplied by at num y plus at y. Looks a long line, but yeah, should do it. Okay, now let's copy these, paste it here, paste it here, but set it to v, set it to here, set it to v, delete the I, and remove the add, and get the corresponding position value. So u dot get at, forgot to say at. Now we're currently looking at this coordinate, so copy this coordinate, paste it here. Okay, is this correct? Think so, hope so. So do the same for these things as well. This part, going to get the v dot get at and this one as well, v dot get at plus, copy this coordinate, paste it here, copy this coordinate, paste it here. Okay, do I get an error? Yes. Const I int dx. It's really hard to see. Okay, I think I cannot use the modulus. Is that so? Okay, I need one more parenthesis here. Nope, that's not it. The other error, num_y, use of undeclared identifier num_y. No, okay, this one. Okay. Anywhere else? At num_y. Get at error ident still have an unidentified num_y. Okay. Okay, so currently I have no errors, but I might going to have some errors. But let's just copy all these and paste it into the right back as well. Just change the condition even or odd here. Okay, and going into the bindings or options, you can change the iterations. This is corresponding to this iteration value. So copy this value here, paste it here to rerun the code, like in this case 50 times. Now let's see if it's gonna work. If I'm seeing the similar result, it's successful. If not, something must be wrong. Okay, hopefully. Alright, it's working. And it's much faster, I think. Let's try to move the obstacle. Yeah, I think it's working. Some weird things happening when I move the obstacle. Let's check that later. And also, if I move the sources, can I move the sources? Yep. How can you also do that? Okay. Looks good. Looks good. So overall, looks good, and I think I can now increase the resolutions to a higher value, like 100. 512 to 256. Still run pretty smoothly. Yep. Now, not really sure about these. The jittering here. Where can I fix that? If I set the initial U value, maybe this is going too fast. Maybe that was why. Or anyway, overall it looks working. It seems like it's working. Now let's also check the pressure value, if I'm getting the right thing. The pressure value is calculated in P, stored in P value. So let's see if I get something. The maximum could be really high. No, it doesn't really look correct, does it? I think It's wrong. Let me check the pressure value. So let's also fix the pressure value. See what I'm doing wrong. The range of the pressure is okay. That's too big. That is too big. Okay. Let's fix that. And that's obviously is related to where I did the projection. So that's where I did wrong, I think. Let's go inside. Let's check the detail. So we have a density, a dt, gravity 0, h value seems a bit big. Maybe this is wrong. I think this should be less than 1. I think. Let me look back at the code. Detail. So it says h is number x divided by width. Let me change this to 1 divided by width. Or, yeah, 1 divided by width. See what happens. Okay, now it looks more like it. Still, looks, the range looks a bit too large to me. Let me check the implementation where I did the calculation. So this is CP. Let's check the density, H and DT. Density is 100, DT is like that, H is like that. So pretty much you got 100 with the CP, I think. Right. This is pretty much more or less 100. Then you are calculating, setting the pressure right here. At P, the current, updating the current P with the CP multiplied by P, right? Which looks correct. Okay. Let me change the density to 1. See if I'm gonna see any changes. Wait a minute. Why I'm not seeing anything here? Because of the density here? Now I am not seeing anything somehow. Let's see. Let's make this. Oops. I was using the width. I wanted to change the density. Sorry. Okay, now. What's the range for the pressure value? It's 52. The maximum 52. Okay. Range isn't that bad. Okay, looks correct. Now I'm not really sure about the units of the density. I didn't really look into that yet, so but at least you could visualize it. In terms of the unit, you need to tweak the initial density value as well as the time step and height, but which is not related to this grid size, so I think I need to fix the unit somehow. Anyway, the simulation looks like this. Interesting. Okay. Now, with having this implemented, you could customize the setup as much as you like. Like you can change where to start the smoke, which direction is the initial directions, how many obstacles you get, how many sources you get. You can add multiple number of obstacles and sources. It's like that. Okay, let's also try to show the vector flow, the vector line. And I'll finish this live. To show the vector lines, you can just visualize the U and V as a direction. So not that hard to do. Point wrangle. Get the U and V, set it to N. So U to the X, V to the Z. And lengthwise, I'm not sure if this is enough, but let's check. And let's copy the line. I mean, copying the line to every point might be too much, but let's just see if it's gonna show something. And let's color this white. Zero, zero, one. Okay, I do see some floors, but too much points. Let's reduce the number of points. If Ix is equal to Ix modulus n is not equal to 0, remove point. It's not removing. Okay, because I haven't set it here. Okay, so X, this is for the X, and let's have another conditions. Or if Iy is not equal to 0. Alright, now I have reduced the number of points. It's much easier to see. Let's have it like that. And merge it with the colored gradient. Maybe I can change the gradient to more colorful one. And transform this a little bit upward so that you can merge it. Okay, let's check. So the vector flow wise looks correct, I think. Alright, so let's see if I move the obstacle manually, what would happen. You could kind of see that it's also updating the vector field, which is what I want, so that's good. Alright, I think it's working just as I want it. Alright. Hi, the fire. Isn't your divergence wrong? Is it? Did I do something wrong here? Let me know where it is wrong. Okay, I'm now looking at the comments. Not sure when it is being written. Let me know if I did something wrong here. Not sure. Well, for now, I think it's working. And let me see if I disable this X-stop or extrapolate, if it's gonna work, since I don't know what's really the purpose for that. Oh, interesting. Is it working? Is there any differences? Let me go back and re-enable it, see the difference. Maybe it's the same. Didn't give much differences, I think. Alright, well that's fine, that's fine. I'll just keep it just in case. Okay, let's make a switch between showing the vector field and not create some toggles. Use OpenCL. Show vector field. Okay, let's copy this one. Paste it to here. Going to show vector field. Paste it to here. Okay, and let's recheck. Okay, right now I'm not using OpenCL, so it's pretty slow. It's VEX based one. Let's enable the OpenCL. Play it. You can see it's much faster. Cool. Now, what obstacle for some play? Let's add some sign animation. this one as well. Yeah, and I think it's working pretty well. And this is pretty much it. Let me know if you have any questions or feedback or some suggestions. Any comment will be grateful. Let's reduce the yeah, I think it's working pretty well. One more thing what I want to add is to control the velocity, control the multiplier for the velocity for the obstacles. Maybe I want to have additional parameter for that. So when I move the obstacles, I'm updating the velocity somewhere around here, right? Somewhere around here. I might want to have some multiplier parameter to control how much it affects, how much the movement of the obstacle affects the vector field. Let's try that. Okay, so let's go back to the controller and copy the velocity multiplier. Probably go from 0 to 5. 5 might be too high, but let's see. So, what if I increase this multiplier to 2? What happens? Not sure if I'm seeing any changes here. Let's also show the obstacle size in color. So I can do that by coloring the obstacle. Should do it later. By checking the O value. If O value is more than 0.5, set the color to cyan. Okay. So the velocity is not really having an effect here. Let me try to increase this to 10. Bit weird things happening here. Okay, let me try to fix this. I think something's wrong here. Let me check the previous implementation, see what I did. Okay. Data obstacle. Okay. Okay. I forgot to use this multiplier here. Need to do that. So let's make a variable called VX, which is this value here, by, and bx is going to be set it to here and here. By is going to be used here and here. Okay. Okay, that's too much. No, that's too fast. So 10 was a bit too much. Let's set it to 2. Okay, looks better. More like it. I can see that now the ball is affecting the vector field, pushing the smoke a bit further. Okay. Yes, that's pretty much it. Let me know if you have any comments. If not, I think it's time for me to stop the live stream. I hope you enjoyed it. I hope you learned something new here. At least I did while I did the implementation, so it was a good exercise for me. Hopefully you found it as the same as well. As always, I am going to upload the file publicly so that you can download it. You can go to the download link from the video description page later when I end the live stream. Okay, so that's pretty much it. I also am doing a Patreon page, so if you are kind enough to support me, that will be great. But every file and video is accessible for free, so don't need to worry. Okay, that's pretty much it. Thank you very much for anyone who joined the live stream. Appreciate it. I hope to see you sometime next week as well. Okay. Good night then, and hope you have a nice weekend. Night.